I'm waiting for somebody or we'll start now. So let's start. So our last speaker is he will speak about fast multivariate multipoint evaluation.
Thank you for being here. And I know that you see the next half an hour as a sort of an obstacle between you and a fancy dinner, so I'll keep it short. So various subset of people here have heard some version of this talk. So if you have already seen this, there's not much that's here for you. So this talk is mostly going to be for people who haven't seen this these days. So please stop me and ask questions. I have 200 slides, literally. I'm not doing it. I don't intend to include stuff. Okay, so this is based on like a various joint work with various subsets of these people. So Kumar, Suman Kokoch, Royego, Prahlad and Ramsar are here. Sima Erdad, Chandrakant Mahapatra, who was a student at IIT Bombay, who is a student for a couple more weeks, I think, and Chris Owens. All right, so what's the question? So the question is the following. So your input, so this is an algorithmic question. Your input is an univariate polynomial. The polynomial has degree less than d in every variable. And this is given to you as a list of coefficients. There's an underlying field. For now, think of your favorite field. It may be, for now, it may be easier to think of the field K as being a finite field for reasons that I'll come to later. Okay, so your input is the coefficient vector of this polynomial, and along with a bunch of points, so a bunch of m tuples over here in time. M is the number of variables. And your goal is to evaluate the polynomial f on these points alpha and alpha. So I'm going to follow these notation, this sort of notation throughout the talk. M, little m is the number of variables, capital N is the number of points you want to evaluate the polynomial, little d is the degree in each variable. So this is an m variate polynomial of degree less than d in each variable, so it's a coefficient vector of length d to the n. So the input is given by a vector of length d to the m plus capital N times m field elements. So, okay, and if this is getting sort of too many parameters, then think of d to the m, think of these two terms as being equal to each other. So capital N is roughly, so the input size is like order n. And there's a nice algorithm to this problem. The first thing you try, you iterate over all points, evaluate the polynomial at a point. And if you look through this, this is roughly capital N times d to the m field of variables. The goal is to solve this problem and to do it faster than what you'd get.
You output all these n f of.
Yeah, I want to evaluate f on these points. Yeah, so the naive algorithm will just iteratively do this, and this is roughly in the regime of parameters that we were thinking about. D to the m is equal to capital N. The input is of size order n, and the running time here is about order n square. So this is a quadratic time algorithm. And what we would like to understand is if we can do this fast. Okay, so can we do this faster? In particular, can we hope for an algorithm whose time complexity is roughly linear? So that's the next. Right, so I said we should think of K as being a finite field in the previous slide. Let me just dwell a little bit on the problem when you ask it over infinite field. So suppose that you have your polynomial and your points are, say, over the field of rational numbers. And in the case of finite fields, our output size was roughly capital N, right? You're evaluating f at alpha 1 to alpha n, so you have capital N field elements. And these are all elements of an underlying finite field K. Let's suppose K is of size Q, so this is n log Q bits of information. You can output it in nearly linear time. But if your problem is over an infinite field like rationals, then the evaluation that you're getting, so f of alpha I may be numbers that are large bit complex. So your output may not even be of size linear in the input. So you have to ask this question a little more carefully if you are over infinite fields. So for instance, suppose your polynomial is x to the d. It's a univariate polynomial. You want to evaluate it at 1 to 3 up to d. So every evaluation apart from f of 1, the bit complexity is at least little d. So the output size is actually quadratic in d. So you can't really go for a linear in d time algorithm. So over infinity, you have to be careful. So there are various versions of this problem that you can ask over infinity. For instance, we could seek an algorithm whose time complexity is linear in the output side. That's the best we can hope for. Or you could seek an algorithm with the guarantee that the input points have small absolute value, and maybe this helps keep the output complexity small. Or maybe we don't want to compute the evaluations exactly. Maybe we want the first 10 bits of all the rational numbers that show up in the evaluation. So some sort of an approximation. Or you could just count field operations. You wouldn't even care about the bit complexity of the field population or the field elements we are generating. Just count the number of field operations. So if you ask this question about infinite fields, there are various versions. Okay. So the version that I will briefly mention will be this version. This is approximate multi-point evaluation. So suppose your field is rational numbers. Again, your input is an univariate polynomial, blah, 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 with rational coefficients, and you have n points. And now your points are guaranteed to be from the unit cube. So every coordinate is at most of absolute value at most 1. And there is an accuracy parameter given to us. And your goal is to basically get the first t bits of your output right. Okay, so every output is a rational number, so you want the first t bits after decimal. Okay, so that's what this version is. So this is what I call approximate multi-point. So I tell you some more things about what's known about this problem, but let's first ask why do we care. And I think the reason to care about this is this. It's a very, very basic and natural algorithm question about polynomials. We use polynomials left, right, and center. We should be able to evaluate them faster than something trivial. But this is a very basic question about polynomials. If this doesn't make you happy, there's a laundry list of potential applications of this. So the current fastest algorithms for many of these problems written in blue here actually go via fast multi-point evaluation. So maybe the most well-studied problem here is this question of univariate polynomial factorization over finite fields. And the current fastest algorithm for this goes via the current fastest algorithm for multi-point evaluation. All right, so yeah, so there are good reasons to care for this problem. So let's see what is most of us. So what we do depends on the number of variables. So in particular, if you are looking at the univariate case, so we have a univariate polynomial and we want to evaluate it at a bunch of points and we want to do faster than trivial. This problem is pretty well understood. So in particular, we know nearly linear time algorithms over essentially polynomials. And the moment you increase the number of variables to beyond 1, so even the bivariate case was much less understood till the beginning. Okay, and this is the case that we are interested in. So m is greater than 1. All right, so let's briefly see what we know about the univariate case. So in the univariate case, the problem is just this: you have a univariate polynomial. It's of degree at most t. It's given to you as a list of coefficients, and you have a bunch of points, and you want to evaluate the polynomial at these points. And the input now has n plus b mechanisms, and you would like an algorithm that's about linear in n plus b, if that's possible. And I want to claim that if the point set in the set of points, if alpha i's are not arbitrary but have some structure, then this is an algorithm you would have seen at some point in your algorithms class. So suppose alpha i's are the roots of unity of some order, then we can do this in nearly linear time. Why? What's a 3-word answer? Fast Fourier transform. So if alpha is the roots of unity, this is exactly computing the discrete Fourier transform order. You can use the FFT. Now, what happens for an arbitrary set of input points? So if you remember FFT and you think about it, you realize that the fast Fourier transform algorithm really relies on the structure of alpha I. It really uses the fact that these are polymorphs of unity of a certain order, and then you square them and you reduce their number from what a capital N to So if alpha is a completely arbitrary, this just breaks down at the start. Nevertheless, in 74, Borodin and Monk gave an algorithm with roughly the same running time. So the running, so FFT is like capital N plus D times log of this number times some sub-logarithmic factor based on what field you are on. And this algorithm of Borodin and Monk has an extra log factor. That's all it has. And it evaluates a polynomial f at alpha 1 to alpha n for arbitrary to alpha 1 to alpha. Okay, so and if you have never seen this, I highly recommend seeing it somewhere. So this is a very, very neat and clever application. If you're not if you're not a part of the FFT fan club, this is one way to get initiated. And yeah, so for approximate univariate multipoint evaluation, this problem was surprisingly open. So we did not know nearly linear time algorithms. By the way, this FFT algorithm, this FFT based algorithm of Borodin and Monk, it's nearly linear time if you count the number of field operations. You look at the bit complexity of it over an infinite field. It's actually not a really linear time algorithm. In fact, we didn't know such an algorithm until this paper of Morrow's from 3 years ago. So what Morrow's does is he gives a nearly linear time algorithm for approximate linear time. And this is again based on approximate FFT and some very, very pretty geometric ideas. Alright, so this is about the univariate case. What do we know about the multivariate case? So, like in the univariate case, in the multivariate case, your input points have some structure. And structure here roughly means that your point set forms a. So this is alpha 1 to alpha n comes from a grid, so it's a product set. Then you can actually build on the univariate algorithm of Borodin and Monk by an induction and get a linear time algorithm, nearly linear time algorithm. So there's an easy nearly linear time algorithm by some induction on another group. But this requires really strong structure from your input points. So they have to be a dense subset of some products. Right, and this particular case uses the univariate case as a basis. The moment your point sets don't have this structure, so if you're looking for an arbitrary point set, there were no non-trivial algorithms known till relatively recent, even for the bivariate case. So in 2004, Muskill and Ziegler designed a slightly faster algorithm. So this is not a linear time algorithm, but this is a sub-quadratic time algorithm. So this does better than the 9 algorithm we discussed, but it doesn't get you linear time. And this algorithm is based on fast rectangular matrix multiplication algorithm. So, and if you, for the bivariate case, the running time is sort of far from quadratic, but if you increase the number of variables, it actually tends towards the quadratic time. Alright, so there was some more recent progress, recent meaning 15 years ago.
So the running time goes down.
Yeah, the running time goes up as the number of variables. So approaches quadratic.
When you say far from quadratic, it's towards linear.
Right. So for the bivariate case, the running time is say about 10 to the 1.5. Okay. And if you increase your number of variables, then it tends towards 2 minus epsilon. Alright, so in 2008, Humans gave an algorithm for this problem. So Humans gave a nearly linear time algorithm for multivariate and multivaluation under some conditions. And its conditions were that the characteristic of the underlying field should be small. And forget about this e to the little open factors, think of these as constants. So if the characteristic is really small, so extensions of F2, F3, F5, F7, fields like that. And the number of variables was small. So in particular, for instance, we didn't have a nearly linear time algorithm for bivariate, trivariate cases. Those problems were solved by this algorithm, provided your underlying field had small characteristics. And shortly after this, Keda and Humans gave a nearly linear time algorithm for this problem over any finite field, provided that the number of variables is small. So if the number of variables is sublinear in the degree, and you are over any finite field, then Keda and Humans algorithm will run Keda. So there was another paper from a few years ago. So this paper gave they gave a nearly linear time algorithm for this problem under some conditions for the field, and they needed the field to be small, and they needed the field to have the field size will have basically q minus 1 will have small dividends for some technical reasons. So this condition doesn't look very natural. And this algorithm, strictly speaking, is not a polynomial time algorithm since the running time is poly in the field size as opposed to poly log. But I mentioned it here because we end up using it later. We were unaware of it. Right, so okay, so let me summarize this. So in particular, if you allow the number of variables to grow, if your number of variables was growing with it wasn't some linear degree, then we did not have a nearly linear time algorithm over any sufficiently large. And this is basically the question that we studied, and this is the focus of the lesson. Any questions about it? Alright, so let me mention some results. So in 2021, with Bhargava, Ghosh, and Mahapatra, we showed that, so we gave a nearly linear time algorithm for this problem, provided the field has small, the underlying field has small characteristic, and it's of not tremendously large size. So if the size of the field is bounded by some tower of fixed height in the degree, and the characteristic is some linear, then you had a nearly linear time algorithm for this problem. So in particular, if you compare it to say Uman's result that I mentioned earlier, we don't have a condition on the number of variables. The number of variables have that. That's it. So shortly after this, with Bhargava, Ghosh, and Uman's, we showed that you can actually get nearly linear time algorithms over any finite field. And there is no condition on the number of variables. So the number of variables can be large. All right, questions? Okay. Yeah, so the degree, you should think of the degree as an asymptotically growing parameter. For example, the degree is constant. For instance, if t is equal to 2. So we are in a multi-linear case, our algorithm not linear. So there are factors hiding inside D, and it's nearly linear. These factors in low degree terms are small only. More recently, with Prahlad, Ramprasad, Ghosh, and Simha, we also designed, so we built on some of these things to get a nearly linear type algorithm for approximate multivariate multipointevaluation. And the running time is this. I don't know if you remember the parameters. So capital N was the number of points, e to the n is the length of the coefficient vector. T is the accuracy, so we want to get the first t bits after a decimal correct in the evaluation. So it's nearly linear in that. And again, D is asymptotic. Okay. So I said too many things. So let me summarize. So in particular, this was prior to our work. This wasn't. So we did not have a linear time and nearly linear time algorithm when the number of variables was growing over any large enough. And our algorithms basically give you this over all finite fields as long as D is growing, and for approximate multivariate multipointevaluation over real rational points. But D has to do. Okay. Questions? All right, I have a table. So you should ignore the last column. You just focus on this column. So both the previous results of Taylor-Emmons and Emmons require the number of variables to be small, and there is no constraint. These almost number of variables. These are independent parameters. So T literally was individually, so these parameters are actually T coupled. T to the n is silent. T to the n is silent. Yeah. So I mean, so you, in particular, T equals 2 is interesting. When T is equal to 2, you're looking at multilinear polynomial. But then you're also saying that n is looking for equating n to n. Capital N. Oh yeah. So, but that's not a constraint. That was an interesting regime of parameters to keep in mind. It's not. All right. So questions. Okay. So let me say something about applications. So there's some black box applications because of connections that this problem has with other algebraic questions. And we get some things there, which I think are not very interesting. But there are two non-black box applications of the algorithm over fields of small characteristics that I think are interesting. So one of them is an application to an algebraic data structure for polynomial evaluation, and the other application is to upper bounds on the rigidity of atom matrices. So if you have not heard of these things, so I'm going to tell you something about the data structure. I will not say anything about it. So what is the data structure? So polynomial evaluation, data structure for polynomial evaluation is the following set. So suppose you have a finite field of size q. Okay. Your data is a univariate polynomial f. So I'm going to give you a univariate polynomial of f of degree d. That's your data. You can do computation on your data, you can process it. And what I want from you is to answer evaluation queries. So you process your data, you write something in memory. Now I come up with a field element alpha and I say, I want to evaluate, I want to compute f alpha. Does your content in memory help me compute? Okay. And so you want to help answer evaluation queries of this kind. And the two resources you will keep in mind is the space complexity, so amount of memory you need to store stuff. And every time I ask you a query, what is the number of cells of this memory that you are going to access? Alright, so there are other resources here that may be of interest. For instance, what is the time to process your data and store stuff? What is the time to do some local computation after you read the queries and so on? But we will not care about. We'll only care about two resources, the amount of space that you need and the query complexity. Alright, so we want to minimize both these parameters. So there are two simple data structures that you can construct. So the first one is the following. So suppose this is your polynomial. And the first easy data structure is that you just store all the coefficients of f in the memory. Alright, and every time I ask you, so I give you an A in the field, I say I want f of A. You just read off all the coefficients and give it and say, well, compute f of A again. I can always do that. And the space complexity of this data structure. So you're storing p field elements over a field of size q, so that's about d log q bits. And the query complexity is also d log q. You have to read the entire content of the memory to answer on basically every query. Right. So if you think a little bit about it, you notice that the space complexity is actually optimal. So here there's some. So you should think of the field size as being polynomially larger than. So think of q as being d to the 100. Okay, so in that case, d log q is the minimum amount of space you actually need for this. So the space complexity of this very silly data structure is optimal. The query complexity. So f of a, the thing is a log q bit quantity. And the query complexity here is 3 times log. So that sounds like a lot. So the query complexity is not great. The space complexity is actually pretty good. It's the best we can hope. So there's a trivial second construction that one could look at. So suppose, so again, this is our data. And what I'm going to store in the memory is the evaluation table of f. So I just take f, I evaluate it on all elements in K, and I store the evaluation tables in the memory. So if I do that, answering queries becomes very easy. So if I give you an A and I say, well, I want to compute f of A, you can just go read a particular cell in the memory and output the content. The space complexity of this data structure is q log. There are two elements, each of them will require a log q bit content. And the query complexity is log 2, because you just go and read one of these. The query complexity in this case is actually log 2. The space complexity is not that big. Again, q is like d to 100. That's the kind of Alright, so here's a natural question. So is there a data structure that achieves the best of both worlds? Meaning that the space complexity is close to optimal and the query complexity is close to optimal. Okay, and perhaps a little surprisingly, Kedla in the result in the paper that I mentioned earlier, actually sort of answered this question. They show that you can actually get a data structure with space complexity pretty close to what you want, and query complexity very, very impressive. It's polynomially larger than what we are doing. Okay, so they almost answered this question. What is the almost about? So to actually say something about it, I'll have to talk about algebraic versus non-algebraic data. So let me start by saying something about algebraic algorithms. So multi-point evaluation is an algebraic problem. You have a polynomial given as a coefficient vector, you have a bunch of inputs, you evaluate the polynomial at the. So and you can the naive algorithm just does some field operations and gives you this value. So algorithms that just do field operations, I'm going to call them algebraic. I'm not going to call it in this, but that's what we do. So, and a data structure is said to be algebraic if all the algorithms involved in the data structure are all algebraic, meaning processing the data, storing content in memory, reading off, doing everything is algebraic. It's the data structure. So, for instance, the naive algorithm for multi-point evaluation that I mentioned, or the fast Fourier transform, or both the simple data structures for polynomial evaluation are actually algebraic. What's a good example of a non-algebraic data structure? It's very hard to come up with. A good, simple example. But in particular, the algorithm of data analysis for multi-point evaluation and the corresponding data structure are both not algebraic. They both do weird things like they will go to a field element, they will access a certain bit of it and do some operations with the bits and then do some computation. So this kind of a bit access is being used. It's not just doing black box field operations with your head. So why do we care about algebraic? So I think they are going strictly for problems that are naturally algebraic, but they could also be useful when working with algebraic models of computation. So I'm being very clear. Talk to me later if you want to know it. All right. So I hope everybody has a sense of intuitive sense of there are certain algorithms for problems like these that are algebraic, and then there are algorithms that I'm not telling you anything about. And ideally, for a problem like polynomial evaluation, it would be nice to have an algebraic data structure that achieves the best of both worlds. Or maybe even data elements like that. And the question is that even possible? Is there something inherently difficult about this problem that only non-algebraic algorithms can get that out of that? And in 95, Mendelssohn showed that if your underlying field is very large, exponentially larger than the median, then there is essentially no algebraic data structure for this problem. That does better than the trivial thing of storing algorithm. You basically end up storing algorithm. That's the best we can do. So Mendelssohn's proof requires Q to be the underlying field to be exponentially large. And he conjectured that the same also holds for small. He didn't say how small the number is. He conjectured that he thinks it's the limitation of his techniques that requires the underlying field to be large. He expects the statement to be global. And one consequence of our algorithm for multi-point evaluation over fields of small characteristics is that you can actually get a data structure for polynomial evaluation that which has nearly linear space complexity and sublinear. That's an algebraic. We require the field to be small, we require the characteristic to be small. We also have a bound on the field size. Some bound on the field size is needed because of Mendelssohn's algorithm. Q is exponentially larger than D, then we can't expect a data structure. But we need a quasi-polynomial bound. I don't know if this is necessary. So it's the query complexity is something like D log Q to the lid log. Alright, the questions? I have 2-3 more minutes. Okay. So let me say I won't talk about Mendelssohn. Let me tell you something about the algorithm. So I want to talk about this algorithm. So this is the algorithm over fields of small characters. Okay. So this is the statement. This algorithm has 2 phases. The first phase is what I call a pre-processing phase. The pre-processing phase of the algorithm is independent of the evaluation point. So I'm not even going to look at alpha or alpha. Just going to look at the coefficient vector of f and the underlying field, and I'm going to do some pre-processing. And the second phase is what I'm going to call local computation phase. So in this phase, I'm going to go to each of alpha I, do some local computation based on the things that are already computed in the pre-processing phase, and write the value of alpha I at the point. I'm going to iterate, but I'm going to do some local computation. Okay, and this structure of the algorithm should already give you data structure bias. And this is why the data structure essentially falls out of this algorithm. Okay, so what is the pre-processing phase? So in the pre-processing phase, we do two things. So the first thing is we construct a magical set S. So this is a set S, this is a subset of K to the N. This has a whole bunch of magical properties. The properties like S is not too large. It's of size roughly linear in the input sense. It's a product set, so it's actually a grid. And then it has this third geometric property. So when you read this, replace this low degree curve by a line. So think of, so let me say, so for every alpha in K to the N, there is a line through alpha that intersects this set S at a large number of points. Okay, so I have a picture later on that I'll show you. But this is what we do. So we construct this set S. It's a small set that's a product set and has this weird geometric property that when put any alpha in K to the N, draw a low degree curve, extremal case a line, and this line is going to intersect this set S in the large number. And then we are going to evaluate F on all points of S. Okay, and the reason we can evaluate F on all points of S is because this is a product set. So for the eventual algorithm, you will need to show
does not even depend on that. Or
S doesn't depend on that. S depends on the field and M and the degree. It doesn't depend on F as all right, and so for now, there are a lot of things here that are unanswered. Does such a set S exist? So that's not clear. But then for this algorithm, we'll have to it's not enough for the set S to exist. We'll have to construct it in linear time. We will have to construct these curves, theta alphas in linear time and so on. All right, so this is the pre-processing phase. Notice that we haven't used the alpha i's here anywhere. And then in the local computation phase, the problem is the following. So we have an alpha, we have some alpha somewhere in K to the N. And we have the value of F on this set S that we have constructed. And we want to find F alpha fast. Okay, and so picture will show you how this is done, and I will stop. Okay, so this is the setup. So this is your set S. This is clearly a grid. We have a point alpha, and there is some sort of a web that you can go from alpha, a low degree curve that intersects the set S at a lot of values of points. And we have the value of F on all these intersected, all the points in all the green points, all the grid points. And we want F of alpha. So how do we do this for somebody who hasn't seen this? So we can interpolate. So the theta alpha is a low degree curve. We look at the univariate polynomial, that is the restriction of F on this curve. That's a low degree polynomial. And for that low degree polynomial, we have a bunch of its evaluations. So we can recover the low degree polynomial, and from that we can do it. So that's basically the goal. If this doesn't give you the running time I promised, it requires a more idea of the model is for that. Okay, so that's it. So it's okay. I think the remote like the loading this is a little bit okay. I have some open questions. Okay.
what is the set S for F to the N?
Good. I have a slide for this. Yeah. So it's basically we are going to pick a subfield of the right side and look at the corresponding vectors.
So that's great, but all subfields are to be on that.
Sure, but I want a subfield of the right side, so I'm going to pick. A B such that F2 to the B is of the right side, whatever that is. And I'm going to look at F2 to B to that. That's my set. Why does it have the curve property? It requires some work, but it does. Yeah, so you work with an appropriate extension. Yeah. Yeah. Very okay. I really have a lot of slides. We've been going to the okay. So there's some open questions. So we don't have an algebraic algorithm of finite fields. That's something I'm very interested in. Over infinite fields, we have a linear time algorithm, nearly linear time algorithm for the approximate version, but I would like an algorithm that is nearly linear time and we count the number of field operations over infinite fields. We don't know how to do that. Some of these geometric ideas can't just work the way it is for silly reasons. Maybe there are ways around it. more applications. I think this is a basic enough problem that there should be more applications for this result on. So now that we can do this for large number of variables, but I don't know. It'd be interesting to have faster algorithms for related problems like multivariate interpolation. So the problem here was that we are given the coefficient vector of a polynomial, we want to compute its evaluations. You can also think of the inverse problem, where we are given evaluations of a multivariate polynomial at a bunch of points. I want to find the coefficient vector of some polynomial that explains this evaluation. We don't know how to do that fast. And the case of constant D is pretty intriguing. So all our algorithms require, they are not merely linear time and multi equals. That's an interesting case. So it'd be great to have it.
This important in the organizers. And information about us. Okay, so thank you. So it's been given up a good day. And so Shivani is going to start that with the feedback form. So this series